Welcome to my video lecture 4 for module 4. Here I'll be reviewing the normal distribution with all the possible cases that you could have under a normal distribution for our course before we get into the video lecture 5, which will be just drilling and doing a lot of examples so you guys could become comfortable with the concept of calculating probabilities under a normal distribution. Now recall that when an experiment is continuous, then the distribution that governs that experiment has to be some kind of a curve, not a histogram. So I'll start with just talking about a very basic misunderstanding, which is pretty common. We talk about experiments, and we say this experiment has a normal distribution. It's like almost using a street language. It's not formally proper. You should say the random variable in this experiment has a normal distribution, but you've heard it says, this experiment is normally distributed, or the data is normally distributed. What does that mean to begin with? First of all, there has to be some kind of a connection between an experiment, and when someone says this experiment, if you graph it, it looks like this. I mean, how do you graph an experiment? How could an experiment look like a curve? Well, to clarify that, what they're talking about is that if you actually construct a probability distribution for that experiment, just like you did it for module 3, but in this case it's continuous, so as we've talked about it before, you can't just list the number of outcomes because there'll be infinitely many of them. But nevertheless, if you do construct, somehow using calculus and more advanced topics, if you actually do construct the probability distribution for an experiment, and then you graph it, and then the graph of that looks like this, then you say that experiment has a normal distribution, because the picture of its probability distribution, instead of looking like this, like it used to look like in module 3, it's going to look like a connected continuous curve. And there's a lot of them, but as I told you before in this course, at this point we'll be learning only the normal distribution of focusing on that. So instead of looking like a histogram, it'd be looking like a bell-shaped curve. So that's what it means when we say an experiment has a normal distribution. It means if you construct its probability distribution, it's going to look something like a normal distribution. Okay, well, that's it. That said, now remember we talked about the fact that the probabilities under a probability distribution always adds up to 1. You remember this from module 3. Now, well, a normal distribution, even though it's continuous, not discrete, but it's still a distribution. So the first and foremost thing that one would have to learn about a normal distribution would be to realize and understand that the probability under the entire thing, or in other words, the area under the whole thing, and I'm talking about this area here. I'm not going to be very exact and accurate in painting it, but you see the idea is that this whole yellow area here is 1. Oops, too thick. Is 1, or basically 100%. And mind you that these two ends, they go on forever, but they get closer and closer to each other. So that's called asymptotic behavior. You don't need to worry about that. That's a calculus concept. But I just want you to know that when you have a full-blown normal distribution, and it is a probability, a valid probability distribution, then the area or the probability under the entire curve must be 100%. Now, normal distribution, as I told you very, very long time ago, beginning of the semester, it's a symmetric distribution, and that's why it's very desirable. Meaning if the whole thing is 100%, if I break it in half, and we always know the center, the center of the normal distribution is always the mean of the experiment. So if I break it in half, then each half will be, because the whole thing is 100%, and it's a symmetric distribution, so obviously each half will be how much, guys? Take a guess. Right, 50%, because half of 100%. So it's pretty clear and obvious that the area or the probability of being below the average in the normal distribution is always 50%. And the probability that you're above the average, which is the upper half, is also 50%. So basically, just by learning that, just by knowing that, you know that anytime you have a normal distribution for any given exercise, the probability that you will be below the mean will always be 0.5. And the probability that you be above the mean will also be 0.5. All right, so these are very simple facts that one would need to know about it. And that's because of symmetry. Very well. Also, one might need to know that, again, I'm sure you guys have read all this on a PowerPoint, but I'm just reviewing it with you before we do a whole bunch of examples because I want you guys to really have an intuitive understanding of the normal distribution. I could have just given you the commands right away from the very beginning and you just do it. It's really four different commands with different type of problems for each one, but it's better to really get an understanding of the shape of the normal distribution is and its properties, so that you're just not blindly calculating values. You actually know and understand the normal distribution. So the area under the whole thing is 100%. If I break it in half, each half is 50%. So it no matter what the experiment is, and it no matter if it's a standard or non-standard normal distribution, meaning if it's in terms of z's or x's, either way, the probability that you're below the average always 50%. The probability you above the average is also 50%. You don't need to know any calculus, you don't need to know any commands, you don't need to know nothing, you just need to know that fact. And remember, that's a fact, not an opinion. Alright guys, so the next thing I want you to understand and comprehend about normal distribution, and because of its symmetric nature, is that if, again, I have the middle, which is the average, the mean, and let's say I'm dealing this time with the z-scores, and I'll review that as well with you guys as soon as I'm done reviewing the properties of a normal distribution. Now, if it's a z-score, it means basically when I say it's a z-axis, it means the middle is always 0 because it's standard. It's experiment independent. So we're not talking about IQs or GPAs or body temperatures. We're just talking about a standard non-application wise distribution. I mean a variable here, which is the z-scores. So if the mean is 0, and let's say I pick a z-score 1.68, and say I find the area or the probability between that number and the center, the average. So say I'm thinking about this area right here between the 1.68 z-score and a 0 z-score. So let's say I'm looking for that area, and at this point we're not going to talk about how to calculate it or how, I'm sure you know how to do it, but I just want to talk about its essence. So let's say I have this area here. So say I have that area, and say I know that the probability of that area is, say, 0.4535. Let's say somehow you know that. Now, if I were to write that as a mathematical problem here, a question and an answer, the question here will be find a probability that your z is between 0 and 1.68. And that's right, that's how you read it. A lot of us read this as p parentheses 0 less than z less than 1.68, which is kind of funny. You don't read this left to right, guys. You read this holistically. So with this, the way you read this and what this means is, what is the probability that z is between these two numbers? Basically, I'm looking for this yellow area. And if you can't see the white arrow, basically I'm looking for this yellow area. That's what this is. So when someone says find a probability that z is between 0 and 1.68, they basically are asking you to find the area between 0 and 1.68 under a normal distribution, which is that yellow area. And let's say you found that to be 0.4535. Now, it turns out, because of the symmetric nature of the normal distribution, which makes it special, if I ask you to find the probability, if I ask you to find a probability that you are at negative 1.68 and 0, you're between negative 1.68 and 0, and I'm going to color that with green. So if I ask you to find that probability, now how would I write this green area as a mathematical question? Well, it would have to say find the probability that z is between negative 1.68 and 0. This time we're talking about this green area, but ironically, again, because it's a symmetric distribution, whether you're 1.68 above the mean or you're 1.68 below the mean, either way, your probability will be the same, 0.4535. So you see, that's why you hear in those, TV scientific shows and stuff, they say, symmetry is very important, because if you have symmetry, a lot of calculations become simplified and you wonder why. Well, every time in a system, in a structure, whether it's business, finance, economics, social science, or astrophysics, or looking for black holes in the universe and the galaxies, symmetry makes people smile, because if you know your system that you're trying to study has symmetry, you need to do half of the calculations you're required to do, because the other half will be the same because of symmetry. Like you see here, it's a clear example of it. If I know that the area between 0 and 1.68 is about 45%, then the area between 0 and minus 1.68 will also be 45%. So you see, I don't have to do the second calculation. Based on the first calculation, I know the second one without doing it. That's the gift of symmetry to structures. Because if you have symmetry, in any given scenario, you always do half of the calculation, so you save a lot of time and money in calculations and big calculations for big companies. So these are the properties, guys: 100%, 50-50, and then symmetric properties of a normal distribution. Very good. I'd like to also talk about some just linguistics about the normal distribution, and then I'll talk about how it breaks down into standard and non-standard and what variables they represent. And then we'll move on to our next video lecture. We'll just be focusing on just doing drilling and doing examples, so you guys could become comfortable with the concept. Now, some terminology very specific to symmetric distributions, guys. Just so you know, this is almost like a foreshadowing for the next module, but it's a good idea to get a feel for it starting this point. If I have a normal distribution, again, it's independent of whether the horizontal axis is x or z at this point. Again, I'm just talking about some terminology about the normal distribution. It has nothing to do whether it's standard or non-standard. They're always called the same, what I'm about to tell you. Now, say I'm interested in the middle area of the normal distribution. I'm assuming that the left side, right side are identical. Forgive the artistic abilities here, guys. So let me just fill this out. And here's my mean. So I want to draw that so you guys can see that. All right, so if I go use a different color here. All right, so this yellow area of shaded, guys, is the area inside, in the belly of the normal distribution, I call it. And say this area is, I don't know, 90%, let's say. Only the yellow area. Now, if that yellow area is 90%, and we obviously know it's symmetric, so which means each half at this point would be how much? 45%. Not that it pertains for what we're talking about here, but I just wanted you to know that. So if the inside area is 90%, and I know, going back to the very beginning, that the whole thing is 100%, now coming back here, if the whole thing is 100%, and I'm telling you the middle is 90%, then how much do you think will be the area or the probability in the tails? So if I were to shade the tails with the green color, and then we'll shade the other side with green colors, and of course these two green areas are the same, right? Because it's symmetry again, correct? That's why it's such a desirable distribution. So the two green areas here I've shaded on both ends of the normal distribution, and they don't call it ends, by the way, they call these tail areas. There's a name for it, which I will share with you. That's why I'm doing this. So if the inside is 90%, then the two tail areas here, both of these, will be 10%, correct? Because the whole thing is 100. If the middle is 90, then whatever that's left is 10%. But because it's symmetric, each one will be correct. 5% or 0.05. So since we don't deal with, I've told you not to deal with decimals in this class, but I'm giving you decimals because it's easy to understand. Remember that we're going to call this 5% 0.05, We're going to call this 90% 0.9, and we're going to call this 5% 0.05 again. So get used to looking at these numbers as decimals, not percentages. Now these things have names. When you have the area of the center of the normal distribution, which is 0.9, the area of the belly of the normal distribution, I call it, that 90%, guys, which is 0.9, that we call the confidence level. And this will become, you'll see that word a lot in the next module, but that's what they call it, the confidence level. And that 10% in the both tails of the normal distribution, which is 0.1, which is the tail, actually combined tail area, we call that the significance level. Now the confidence level doesn't have a symbolic thing to it, but significance level has a symbol associated with it or attached to it. Significance level is called alpha. Some people call it Nemo, but we call it alpha. And that's what alpha is. It's a significance level, which is, what's a significance level? Well, it's the area in the tail, in both tails of the normal distribution. So an area in one tail will be alpha over 2. The area at the bottom tail will also be alpha over 2. And once they name the significance level alpha, then confidence level by definition is 1 minus alpha. So here, the labeling has been given to the significance level, and the confidence level has been written in terms of that. So to make this clean one more time for you, because it's extremely important for you to be comfortable with these names, I'm going to draw it again. And I'm going to take the middle this time, 95%. All right. Okay, so which means the tail areas will be 5% combined. So each one of them will be half of 5%, which is 2.5%, which is 0.025, 0.025. And I'm going to write my 95% with decimals, 0.95. So what is this called? Just that one area on the left. Very good, alpha over 2. What is this one called? The area to the right. Very good, alpha over 2. And how about this middle belly area? What's that called? 1 minus alpha. Very good. So those are the variable names for it. 1 minus alpha is called the confidence level. And the 2 alpha over 2's combined are known as significance level. And combined, they're alpha, which break into 2 symmetric pieces. So it's extremely important for us to know the relationship between the confidence level and the significance level. Very good. Now the last thing I wanted to review with you guys is the breakdown on the types of variables we deal with, random variables, when it comes to normal distribution. When we're talking about calculations for the normal distribution, we'll be talking about two types of random variables. Will be called the standard normal distribution and a non-standard normal distribution. Now, the standard normal distribution, now mind you, I just want to let you know, they both look like a normal distribution, so the looks of it, the shape never changes. So standard, non-standard both look the same. Now, standard normal distribution is, in more advanced courses, you'll see them labeled as Z approximated as N01. It's a mathematically heavy notation. I'll tell you basically what that means. And for a non-standard, you'll see it X is distributed as N mu sigma. So basically they call a standard normal distribution an N01, and they call a non-standard normal distribution N mu sigma for whatever mu and sigma are in whatever particular experiment it is you're talking about. Now, what does it mean to say that a standard normal distribution is Z approximated by an N01 or distributed as an N01? What does that mean? It means if you draw the normal distribution in this scenario, your horizontal axis will be the z-axis, your vertical axis will be the probability axis, and Here's how your normal distribution would look like. Forgive the art. And we call that an N01 because the mean is 0 and standard deviation is distributed in units of 1. So it'll be 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. So that's a standard normal distribution because of that scaling. So it basically has to do with the scaling of what variable you're talking about. For a non-standard normal distribution, again, you notice the shape is the same, but now my horizontal axis is the x-axis. The vertical axis stays being the p-axis. Then if I draw the normal distribution here, now the mean here is not 0 anymore because it's non-standard, meaning it's based on some kind of an experiment. The standard one is not based on some kind of an experiment. It's just raw basic numbers. Z-scores that is. But for a non-standard normal distribution, you have to have some kind of an experiment like IQs, GPAs, body temperatures. So going with our usual example of IQs, then the center is not going to be 0. The center is going to be mu, but mu in whatever example I'm giving you will say is 100, which is the IQs. And then the standard deviation is 15, which means we go in units of 15. So if that's 100, the next one will be 115, the next one will be 130, and so on. And that's the scale for this one. And on this side, you go minus 15. So you go lower than 100. So you go from 100 to 85 to 70, and so on. And that, guys, we call a non-standard normal distribution. Very good. And the last thing I'm going to review here is that each one of these standard and non-standard normal distribution in module 4 for us come to you with 2 different questions, 2 different calculations, 2 different Excel commands in general. Now, if I have a standard normal distribution, which means it's in terms of z's, and they usually don't draw the horizontal axes, the vertical axes much, but I'm going to just draw it here to be safe. And that's a probability axis. So if I have a standard normal distribution labeled as N01, standard normal distribution, I'm going to be asked to find 2 things. I'm going to say find, and I'm going to give you the 2 examples here on the side. So I could ask you to say, I'm going to draw a smaller picture for you. So I could be asking you A, say 1.84. I could be asking you to give me the probability that z is less than 1.84. That's one question. Probability that z is less than 1.84. We call this the forward problem, meaning I've given you the z-score and I'm asking you to find a probability that's below it. The second question I could ask you, which is the reverse problem, is that I could give you a normal distribution again, a standard normal distribution. Again, that's the z-axis, that's the p-axis. And this time, instead of giving you a z-score here, I'm going to say, well, I don't know what that z-score is, but I know that the area above it is 10%. What is that z-score? This is the inverse problem in the standard normal distribution. Basically, I've given you p and I'm asking you to find z. In the example above it, in here, I was giving you the z-score and I was asking you to figure out the area. In this exercise, in the second one, I've given you the area and I'm asking you to find the z-score. This is called the inverse problem. And this, in the syntax of Excel, it's called the distribution problem. So any command that has dist in it solves the forward problem. Any command that has inverse in it will solve the inverse problem. And the same thing is true with a non-standard normal distribution. And I'm going to try to fit it all in one page so you guys could see it. For a non-standard normal distribution, we're dealing with n mu sigma, so it's not 0 and 1 anymore. So now it's say 115 for if I want to pick a specific example. That's a non-standard normal distribution, which means obviously it's in terms of x's. And now if I draw my normal distribution here, my center is not 0 anymore, it's the mean. which is 100 in this case. And that basically boils down to two questions. The forward question for non-standard, which is the dist command question. That's if I ask you to find some kind of a probability where I've given you the x value. So I'll say, guys, what would be the probability that someone's IQ will be above 87, let's say. So basically I'm asking you guys to give me that probability, that area right there. We call this the forward problem. I've given you, and that's x, and that's p. So here I've given you x, and I'm asking you to find p. That's the forward problem, the dist command problem. And I could also reverse that on you, or invert it, and give you the inverse problem. Again, that's x, and that's p. And I could say, okay, I want you to give me the x value. Let's try a different one here. I'll give you give me the x value that will put somebody in the bottom 5% of the normal distribution. So you notice here is the inverse problem for a non-standard. I've given you the probability, and I'm asking you to find x. Whereas in the example above it, I had given you x, and I was asking you for probability. So one more time, N01 standard normal distribution is in terms of z's, and you'll have two questions associated with it. The forward question, which means I've given you z, and I'm asking you for p. That's a forward problem, and on Excel we call that the dist command, D-I-S-T, and you'll see, and you've seen how the command has dist in it, norm.dist. And the second scenario would be given p, find z, and that's the inverse problem for a standard normal distribution, standard inverse, standard distribution. And then for a non-standard normal distribution, mu sigma, that's in terms of x's, non-standard normal distribution. And here I have two scenarios. Given x, find p, that's a non-standard dist. And then given p, find x, that's the inverse non-standard problem. So I think I've reviewed this enough with you guys, and I basically told you everything I needed to tell you in terms of terminology and like understanding of the structure here. On my next video, I will be doing a lot of drilling and a lot of examples so we could actually see all these theories to work. Thank you, and see you soon.